This is AP Calculus BC, and in this video, I am going to talk about section 5.7, which is about rectilinear motion, and I'm also going to talk about section 5.8, which is about average function value. So this should be fairly quick video compared to the most recent ones because, especially as it pertains to the motion, we've done a lot of this stuff as we've been going through this semester. So these are relationships that you should be fairly familiar with. And as I've been going through previous sections, I've been alluding to some of these topics that are in this section. So in section 5.7, when we talk about these motion problems, really what we're talking about are the same relationships that we had when we were talking about these same types of motion problems with derivatives: position, velocity, and acceleration. So we know if we take the derivative of position, we get velocity. If we take the derivative of velocity, we get acceleration. Now we're just looking at that in reverse. So if I take the integral of acceleration, I'm going to get velocity. If I take the integral of velocity, I'm going to get position. Okay, so in addition to that, we've discussed displacement and distance traveled a little bit in a couple of the previous sections. When I talk about integrating a velocity function, remember that's just a rate function. So when I integrate a rate function, I'm getting the net change in whatever that function is measuring. So you can see here, I've got my velocity function being measured, and notice what ends up happening: position at time 2 minus position at time 1. That's the net change in the position. Also, we've got distance traveled over a time interval. And we talked about this when we were discussing total area, the idea of total area. So if I want to find the total distance an object traveled, I don't want to be taking direction into account in terms of how I'm measuring the distance. So what we do is we just take the absolute value of the velocity and we integrate over our time interval, and that'll give us total distance. Now remember, this whole idea of using an absolute value, when we have a calculator, we can do it that way. When we don't have a calculator, we have to account for where is the velocity positive and where is the velocity negative and break our integral into those different parts. Okay, so here's a really simple example just to get you used to this idea. It says a particle travels with velocity t minus 2 sine t meters per second for the time interval 0 to 4 seconds. So part A, it says, what's the particle's displacement? Well, if I want to find the displacement, remember, all I'm going to do is integrate the velocity function. And I told you this last time, I just want to reinforce this idea. Since the velocity function has been defined up here as v of t, I'm not going to rewrite this because this would be a calculator question at this point for us. So I'm just going to write v of t dt is what I'm integrating. And then I would plug this into the calculator, and that would give me a displacement of about negative 1.4495. And again, if I'm not sure about the units, I can always verify. Velocity was in meters per second. dt would be in seconds. So this should end up being in meters. Okay, and then we just talked a minute ago about distance traveled. So when I find the distance, I want to take the absolute value of the velocity. So in this case, I'm going to integrate from 0 to 4, the absolute value of this velocity function, and that would give me approximately 1.914 meters. Notice that these two values are not the same. The displacement and the distance are actually very different values, and it's because we have parts of our interval where we're moving in the positive direction and parts of our interval where we're moving in the negative direction. So the distance takes all of that out of it. When we are thinking about displacement, the positive and the negative matter. All right, when we are looking at velocity curves, keep in mind essentially what we're doing here. So we went through the last problem, and in the last problem, it really did all of this for us when we did this on the calculator. But now we're going to look at this from a graphical perspective, what's really going on when we talk about displacement versus distance. So when I'm talking about a displacement, let's say I've got a velocity graph here. You can see this is labeled as V. If I'm trying to find the displacement, these areas above the time axis would be treated as positive. That means we moved in the positive direction. And this one, area 2, would be treated as a negative because I'm moving in the negative direction. So notice down here for displacement, area 1 minus area 2 plus area 3 would give me displacement. But for distance traveled, I just want the total of all those areas. So we just add the 3 together. Okay, so that was graphically what was going on those 2 questions where we did them on the calculator. That's kind of the main idea behind what's happening. Okay, so let's take a look at just a couple more graphs here to reinforce that idea. Compare the displacement to the total distance traveled for the velocity graphs below. Okay, so notice here on graph A, you can see our displacement and our distance are going to be the same because that graph is always above the time axis. So my displacement here is just the area of that triangle, which would be 2, and that means my distance is going to be the same because they're both positive. When I look at the second graph, you can see my displacement this time is going to be negative. And so I know it's going to be -2. It's got the same shape as the previous graph. But the distance here is still the same. It's still a +2 because it doesn't matter which direction I'm moving in. And now for the last one, if I'm looking at displacement, notice that this area and this this area are basically the same. So if I were to combine those 2 together, I would get a displacement of 0. And then for my distance, though, the distance, I would have to add both of those triangles together. And each of them is got a base of 2, a height of 1. So in the end, I'm going to get a total between those 2 triangles of an area of 2. Okay, so what I've got next here is another function defined by an integral question. And what this one is we've got position is being defined as the integral of this f function. So notice this is always the key to these problems. This is like what we did in the fundamental theorem of calculus section. So what I'm trying to do here is answer some questions about position, velocity, and acceleration based on that definition and based on the graph that I'm given. So if I were going to solve this problem out, just like I mentioned on the last one of these that we went through in the fundamental theorem of calculus video, the first thing I always do is label what this graph represents. And when we're looking at an application like these motion problems, it's really helpful to know which of the 3 functions am I looking at, a position graph, a velocity graph, or an acceleration graph. And you can see here, in this case, this would be my velocity graph. So like I said before, I always write that on the graph, and I usually circle it just so every time I look at that graph, I'm remembering that in this problem, I should be interpreting this as the velocity graph. Now, once that's been established, the rest of this just turns into same type of motion problems that we've already been doing. So for example, part A, what is the particular velocity at time is equal to 5? Well, we know we're looking at the velocity graph, so the velocity at time 5 is just going to be equal to 2 because I'm just looking at this coordinate. Okay, so pretty simple. B, is the acceleration of the particle at time equals 5 positive or negative? Well, remember, acceleration would be the slope of the velocity graph, so I can tell in this case that the acceleration at time 5 is going to be negative. So you can either write out that the acceleration is negative, or you could do like I did here, indicating the acceleration at time 5 is less than 0. C, what is the particle's position at time 3? Okay, so remember, this is the velocity graph. Now, what's not directly stated here is the initial position, but it's implied within the circled function definition that I have. Because if you think about this, the position at time 0 would be the integral from 0 to 0 of f of x dx, right? So that's telling me that the initial position is 0. So if I can find the area underneath this curve between 0 and 3, that's going to give me the final position because I'm just adding that area to the 0 position that we started with. And you can see that triangle is got a base of 3, a height of 3. So in this case, my position at time 3 would just be 9/2. D, it says, at what time during the first 9 seconds does the position have its largest value? So even though we're looking at a motion problem, we're still thinking about this in the same way as when we were analyzing the graphs of the function, the derivative, and the second derivative. If I'm looking for a maximum, I need the derivative to be going from positive to negative. And you can see that's happening here at time is equal to 6. So they didn't ask us to justify our answer, but that's how we would justify our answer if we needed to. So we would say it's at time equals 6 because at that point the velocity went from positive to negative. And that's the only maximum on our interval as well. E, approximately when is the acceleration 0? Okay, so remember the acceleration would be the slope of this graph. So we're looking for horizontal tangents. You can see we have one here and one here. So it looks like approximately time is 4 and time is 7. Okay, and it's the same thing. If I were to explain why I know that is the answer, I would explain that the graph of the velocity has horizontal tangents at those points. F, when is the particle moving toward the origin and away from the origin? Okay, so again, knowing this initial position is really important on these types of questions because I need to know where am I starting. So since I started at the origin, my position is 0. Regardless of which way I move at the beginning of this velocity graph, I have to be moving away from the origin. And in this case, you can see we're moving in the positive direction, but we're definitely moving away from the origin on that first time interval. So I'm going to be moving away on the time interval from 0 to 6. And then you can see once we get to time is 6, the velocity switches signs. So now we're moving in the opposite direction. So we have to be going back toward the origin on that last time interval. So that would be on the time interval from 6 to 9. All right, and then the last question, on which side of the origin does the particle lie at time is equal to 9? Well, now we've got to understand how to interpret this graph in terms of the integral value. So look at the time interval from 0 to 6. We're looking at all of this area here. And then look at the time interval from 6 to 9. You can see we've got that another area in the negative region here. But the blue region that I have there is much, much larger than the red region. So I can tell that a net result is I've moved in the positive direction. So as a result of that, I would say I'm on the positive side. And again, if I needed to explain how I know that, I would say the integral from 0 to 6 is greater than the integral from 6 to 9, and I know I started at position 0. All right, so one last problem here. When it comes to the homework assignment, you're going to have a lot of different types of questions you're going to have to answer, but keep in mind, it's still the same things that we did back when we were talking about derivatives. The only difference now is you might have to use some integrals to solve these questions out, and this one uses antiderivatives or indefinite integrals. A particle moving along a straight line is accelerating at a constant rate of 5 meters per second squared. Find the initial velocity if the particle moves 60 meters in the first 4 seconds. Okay, so think about your initial information here. We know our acceleration is 5 meters per second squared. Okay, so from that, I can get my velocity function, which would be 5t plus c. I just took the antiderivative of the acceleration. Now, notice it says find the initial velocity if the particle moves 60 meters in the first 4 seconds. I don't know what this c value is yet, and I don't really have any way that I can identify what the c value is because they didn't give us anything about the velocity at any point in time. So I'm going to have to work off of my position function. And my position function would be the antiderivative here, 5 halves t squared plus ct plus d. And remember, with these constants, you can use C1, C2, you can use whatever you want. The main thing is make sure you're distinguishing between the first constant value, the first arbitrary constant, and the second arbitrary constant. Now, notice they gave me a point in time here. They told me that the particle moves 60 meters in the first 4 seconds. Well, that gives me 1 point in time, but I have 2 unknowns. So even though it's not directly stated here, I have to figure out a second point that I can use. And what we can use here is the position at time 0. So the position at time 0, we can just assume that it's 0. And if that's the case, if the position at time 0 is 0, that means that the d value also has to be 0. And now we can use the position at time 4 that we were given, and we know that it's supposed to move 60 meters in the first 4 seconds. So I'm going to plug 4 in, and that's going to give me 5 halves t squared would be 40 plus 4 times c. And I know the d is 0, so that's going to have to end up being 60. And that will end up letting me solve for the c value. So that means c is 5. And from that, remember on this velocity function, if I plug in velocity at time 0, it's going to give me c. So that means that the initial velocity would be the same as the c value, which would be 5 meters per second. Okay, so that's exactly the same kind of stuff that we did back a few days back when we were just talking about indefinite integrals and we were talking about general solutions versus particular solutions. It's the exact same idea. It's just that now we're looking at it in more of a problem-solving context. In particular, we're talking about motion problems. Okay, so the other section that I have here for you, and we're going through 2 sections today because both of these are pretty simple and straightforward. So in this section, we're going to talk about average value of a function. So when we talk about average function value, we've thought about average rate of change before, but we never thought about it from an integral perspective. So if you look at this, you can see how from an integral perspective, this is still the same thing we were doing before. Before, when we were looking at something like average velocity or an average rate of change, we would do change in position over change in time. Well, another way we could do that or think of it is like you see here, if I integrate my velocity function, I know that's going to give me a displacement. And so that's essentially what we're looking at here. If I were to integrate the velocity function and get the displacement, you can see this, that's actually the numerator of my average rate of change as a slope, as we thought about it before. So essentially what ends up happening is if I want the average velocity, yes, I can do slope formula, but I can also do it like this. Integral of the velocity function, which would end up giving me position at time 1 minus position at time 2, divided by the change in time. Okay, so that's really what our average function value is. Now, there's other ways we can look at it, and I'll show you how we can do this from a geometric perspective. But the main idea is if I want to find the average value of a function, I'm going to integrate that function on my interval, and then I'm going to divide by the length of the interval. Okay, so geometrically, here's what's going on when we do that. So if I integrate, let's say, this f of x function on the interval a to b, that's going to give me all this area in here, right? So all of this would be that integral. So what we're doing is saying, take this irregularly shaped region, and rather than treating it as an irregular shape, we're going to treat it as a rectangle. So we're going to find that total area, and then we're going to divide by the length of the base. And what it's going to leave me with is what you see here, that height of that rectangle, which is our average function value. Okay, so it's a little different than when you have done average in the past, when you think of like a statistical mean, when you add up all your points and you divide by how many points you have. Well, here we have an infinite number of points where we have function values, so we can't really calculate in the same way as what you've done in statistics. So we have to have a different way to account for all of the points, and that's what's happening when we take the integral and divide by the length of the base. Okay, so I've just got a couple of quick examples here for you on this topic, and these are pretty easy, and you'll see that when we deal with average function value, this is not really something that should challenge you that much, as long as you can get your head around conceptually what's happening when you find that average function value. So this is find the average value of the function x squared plus 4 on the interval 0 to 3. So sometimes you'll see it written like this, f with the subscript average. So my average function value is going to be 1 over 3 minus 0. So I'm dividing by the length of the base there, times the integral from 0 to 3 of x squared plus 4 dx. Okay, so remember, when I take the integral of x squared plus 4 dx, that's basically going to give me the change in the antiderivative function divided by now the length of that base. And that's going to be like the change in y over the change in x, or my average rate of change. So in the end, this turns out to be 7. Okay, so very simple to solve that integral out. The last part of this, it says, where is f of x exactly equal to 7? And then it says, use your calculator to verify your solution graphically. Well, where's the function equal to 7? My function was x squared plus 4. So when is 7 equal to x squared plus 4? Well, x squared would be equal to 3 here. That means x is equal to plus or minus square root of 3. Now, a lot of people would give that as their answer. Remember, we're looking at this time interval, 0 to 3. So for us, that means that x would be equal to the square root of 3 on the interval from 0 to 3. What we've just done there is we've just applied what we call the mean value theorem for integrals. So what the mean value theorem for integrals is essentially, if I were to take my average function value on some interval, if my function is integrable on that entire interval, then at some point, the average function value has to equal the actual function value. And in this case, you can see that occurs at the point where x is equal to the square root of 3. So we don't really have to remember that theorem or remember the name of it or anything, but there's a mean value theorem for derivatives and there's a mean value theorem for integrals. Okay, so as far as the homework goes, pay really close attention to those motion problems. Like I've mentioned to you before, we're going to be doing motion problems throughout the year. So you've got to get really, really comfortable with these relationships from a derivative perspective and then from an integral perspective. And once you have it down, these become very, very simple problems. And then for the average function value, I don't really think of this as a formula that I memorize. I try to think about geometrically what's happening. And if I can remember geometrically what's happening, what's shown in this graph is that I'm taking an entire area and dividing by the length of the base, then I don't have to remember a formula. I just remember, okay, how do I find that area? I take the integral, and then dividing by the base gives me the height of the rectangle.